So today, I think I said we were going to skip to part 5, but we have to do 3 before we can do, anyway, so we're going to do 3, maybe on to 5. I'm trying to pick up some time here. Tomorrow's lab, I said 312, it's 302. So tomorrow's lab will be in 302. I will put it on the chem lab door just in case you come, and so you know where we are. It's experiment 17, and basically it's what part 4 lecture would be. In a nutshell, we talked about balancing the equations using the inspection, trial and error, and we're going to look at balancing the equations a different way. So Friday then, we're going to need to finish up, we'll need to do lecture. So there are 6 parts in Unit 5. And then Monday, there's no class. This class won't meet, but if you have a class that starts on an hour that is odd, not as in strange, but odd as in odd and even, then you'll have a final on Monday. Your final is on Wednesday, and it's going to be in this room for 2 hours. Nobody told me that they couldn't go the full 2 hours. Remember, I kind of mentioned that actually instructors are only supposed to give an hour and a half, so students have a half an hour transition time. So somebody let me know if you don't think that's fair because you have to be somewhere else. So I was thinking about your notes, and I always like to try different things if you want. Now, if you want, you can bring a blank piece of paper, paper with lines with notes front and back. If you want, you can take this sheet that I gave out to you, because I think this is what I would do, and you can actually write in the margins and write on the back and bring this with you. I think that would be awesome, because you could look these up. You're like, now, oh my gosh, what the heck was that? You look it up and you write it in a note. You can actually, or you can bring a blank sheet of, that's what I was going to say, bring a blank sheet of paper. If you bring a blank sheet of paper, for sure, one way or the other, I'm going to have these on Wednesday, and you can figure that. Does that make sense? I love that. Okay. So I gave out to you some multiple choice questions. So I can't guarantee any of those will make it to the final, but they kind of give you a place to start. And then the last section will be the problems. And it's kind of like in Chem 1, where you will see Unit 5 questions, some like in the multiple choice and the problems. So keep working those homework problems. Speaking of, I finally, late last night got part 2 homework posted. I'm close to getting part 3 homework done. So I had one of our daughter's girlfriends was over, and she's like, I bet your students like that you have to work so hard. I'm like, yeah. This semester, I'm working hard to keep up with you guys. All right, so there you go. I like this topic. Let's see if you like it. There's different types of chemical reactions. A chemical reaction has occurred if what you start with is different than what you end with. You use chemical equations to represent chemical reactions. There's a special type of chemical reaction called a redox reaction, or an oxidation reduction reaction, same thing. Okay. And so we need to kind of talk about what happens with the redox reaction. The type of reaction, for instance, we've done a lot with is the exchange reaction, where your cation and your anion switch partners. That's an exchange reaction. It's a different type of reaction. Okay? So redox reactions. In order to understand redox reactions, we need to understand or be able to assign what's called oxidation numbers. Now, there's 2 ways to assign oxidation numbers to, and you'll pick up as we go along, but basically you'll have a formula for stuff, and for each atom will have its own cute little oxidation number. There's 2 ways to do that. I'm going to kind of drag you through this first way, and then I'm going to kind of show you some shortcut ways. Okay, so oxidation numbers. We can think of the oxidation number that we assign an atom as being actually the charge on that atom if it was pushed to the ionic limit. So I'll kind of show you what that looks like. So this sort of thinking through, so we assign oxidation numbers to each little atom that we're dealing with. It's not a real situation, but it's just kind of a thought situation. And it assumes that all of the bonds are ionic. Ionic bonds where electrons were transferred. So it assumes that, okay? Which is kind of weird in and of itself. Let's see. For instance, so we're used to seeing kind of like things with charges on them. So for instance, when sulfur, picks up 2 electrons, it forms an S2-. 2- is its oxidation number. Okay. When calcium loses 2 electrons to get the electron configuration like argon, okay, calcium, it becomes a Ca plus 2. Plus 2 is its oxidation number. Okay, so it's really not that strange. So I'm gonna kind of talk you through an example though. Those are pretty obvious. They're not always so obvious. So again, we're gonna assume that the electrons are transferred with the bonds, okay? Even though they're not. So in order to have this work, you need to remember electronegativity. So electronegativity, actually, if this is I'll just put group A elements. Electronegativity increases. The symbol for electronegativity is the Greek letter chi. Remember that? So electronegativity increases going from left to right, and electronegativity increases going up the group. That's the trend in electronegativity. We use the Pauling value for the electronegativities. It's the tug of war for electrons, remember? Something with a high electronegativity tugs electrons to itself. Okay? Okay. So let's see what this looks like. Again, I'm going to kind of pull you through this approach, and then actually there's an even easier approach. So we're going to pick on one molecule, and for that molecule, we're going to come up with an oxidation number for an atom, and we're going to do that by taking the number of valence electrons associated with the atom. Now, valence electrons come from the group number, which I don't like this periodic table because I need to change it, but so that's the group number for group A elements. So the periodic table that you have in your, your notes or whatever, they have 1A, 2A, 1 valence electron, 2 valence electrons, 3A, 4A, 5A, 6A, 7A, 8A. So for instance, 5A nitrogen, you're looking at 5 valence electrons. So that's that number. And then the next number, you have to see how it's situated in the molecule. It's the number of valence electrons at the ionic limit. So it's the number of valence electrons, assuming that all bonds are ionic. And you're going to assume that the atom that has the higher electronegativity will get custody of the electrons. So it's kind of a weird sort of deal. So here's what that looks like. We're going to pick on this one. In a minute, the couple slides, we're going to basically break kind of. We know in drawing Lewis structures, every time you see a dash, you have 2 electrons. So looking at carbon and chlorine, who's going to get these 2 electrons? Who's more electronegative? Well, it's a little hard to tell, but I'm thinking chlorine. Okay, I know it increases as you go up. Fluorine will be even more than chlorine, but carbon's way over here. So the fact that chlorine's more electronegative, actually those 2 electrons are going to go to chlorine. These 2 electrons are going to go to that chlorine. What about carbon and oxygen? Oxygen's more electronegative. So how many electrons does it get? 4. So you're going to see 4 electrons withdraw. You're going to see the carbon doesn't have any electrons. Okay? That's exactly what this is showing. So those 2 electrons went to the chlorine, those went to chlorine, those 4 electrons went to the oxygen. Why? Because it's more electronegative. Now we're ready to apply that little formula. So you guys, let's see, carbon is a 4A. 1, 2, 3, 4, 4A. So the first number is going to be 4 for carbon. Chlorine is a 7A. So it's going to be 7 for chlorine. And oxygen is a 6A. So it's going to be 6 for oxygen. So here's what it looks like. So for carbon, we take the number of valence electrons on a normal carbon atom minus the number of valence electrons in this particular structure, like an ionic limit. So 4 minus 0, it's a plus 4. That's its oxidation number. Okay. For oxygen, it's a 6A element, so it has 6 valence electrons normally. And in this case, because it was double bonded to the carbon and it's more electronegative, it got custody of those 4 electrons. So actually, in this case, you're looking at 8. 2, 4, 6, 8. 8. So 6 minus 2 is minus 2. That's its oxidation number. And for the chlorines, it looks like this. Group 7A, so it has 7 valence electrons for normal chlorine. Here, because it got the 2 electrons and more electronegative, 2 electrons associated with that sigma bond, Now you're looking at 8. Okay, so 7 minus 8 is negative 1. One of the rules about, One of the rules about assigning oxidation numbers is if you have a neutral molecule, which this is a neutral molecule, then actually the oxidation numbers of the individual atoms should add up to be equal to 0. How are we doing? So minus 2, minus 1, that's minus 4, plus 4. It's 0. Again, that's the belated way. These are some rules that you'll be applying as you look at like a formula and start to kind of pick out what the oxidation numbers are for everything. So here we go. An oxidation number for an element, if it's in its free uncombined elemental form, is 0, zilch. So that means if you have solid iron, 0. If you have, actually this also applies to if you have hydrogen gas, H2 gas. It's combined, you have 2 hydrogens combined, but it's uncombined with anything else. So that's also 0. It's oxidation number. Sometimes oxidation number and oxidation state are used interchangeably. The oxidation number or oxidation state of a monoatomic ion is simply the charge on the ion. So that's like when I went over here. The halogens we know form a -1. Their oxidation is going to be -1. The group 2A elements a +2. Oxidation number or oxidation state +2. So those are easy. The oxidation number of an atom in a polyatomic ion composed of only one element is equal to the charge on the ion divided by the number of atoms in that formula. The biggest thing, or the one that comes to mind, for instance, is, remember, here's the second one, H2, Hg, mercury, 2 plus. Oh, I just hate that polyatomic ion. But you can apply this rule here. So, of course, that's a molecule. It's a polyatomic ion. You don't break, you don't mess with that bond there. It runs around with a +2 charge. We call that mercury 1, actually. And according to this rule, it says that we have 2 atoms that make up that polyatomic ion. Do you guys buy this? That each one of those atoms is a +1. That's it. Another one I think that's coming up that fits this rule is the triiodide polyatomic ion, and I don't think we did much with that in Chem 1. But actually, that's I3 with a -1. Like what? So again, it's a polyatomic ion, so you have 3 iodides running around with a -1 charge. So what do you think each one, what's the oxidation number for each one of those? It feels weird. They don't have to be whole numbers. minus 1/3 across the board. Okay, so that's an application. It's equal to the charge on the ion divided by the number of atoms in that formula. That's it. So there are 2 examples. Here's another one. This deals with hydrogen. We use this a lot. So hydrogen is usually a +1. Usually. Unless it's combined with a metal in, it's combined, and that's the only other thing it's combined with, like a metal, what we call metal hydride. Okay. So remember, these are the metals. And then it's a -1, but almost always it's a +1. You know, I used to talk to someone about you can hang your hat on that. You can hang your hat on that. So a lot of hydrogen. The next one's oxygen. We have a lot of oxygen. Oxygen is almost always a -2, which actually is consistent with kind of how we find it on the periodic table. It picks up 2 electrons, okay, forms a -2 anion, and the charge then would be its oxidation number or its oxidation state. But this says even if oxygen is embedded into something where it's not an ionic compound, like an alcohol or something like that. Exceptions, excuse me, are when it forms a it's combined with another oxygen atom to form a high peroxide link. All right. This actually is what I just told you a minute ago when we did that example of kind of coming up with oxidation numbers for everything in that CCl2O. I said that in total, they have to be equal to 0. We use this rule a lot. Now, if you're trying to find the oxidation numbers of something that's a polyatomic ion, guess what? When you add up all the individual oxidation numbers, they should be equal to the charge on that ion. That works. Okay, so let's do some examples. This actually is rule number 1, where, and I think I mentioned this, H2 are 2 hydrogen atoms joined together in their uncombined with anything else elemental form. So the oxidation number of each one of those hydrogens is 0. You guys already have these? The oxidation number of magnesium, 0. Rule number 1. Oxidation number of each of those phosphorus atoms in P4. And you may or may not know this, but actually, well, I guess it doesn't matter. It's in its uncombined elemental form. And here, again, uncombined doesn't mean uncombined with any other atom. It just means uncombined with any other atom with this other different element. What do you think? The oxidation number. +1. 1 plus 1, exactly. What's the oxidation number for here? -3. Yep, you got it. I did this one together. What did I say was the oxidation number for each one of those Hg atoms? +1, perfect. They are individually +1, you got it. And then I did this one too. What I say is the oxidation number for each of those individual hydrogen atoms. -1/3. As crazy as it feels, as crazy as it sounds. You got it. So what about, kind of like we did in the first example, when you have 3 atoms like this, you have to be able to say what's the oxidation number of each of those hydrogens and the oxygen. So what's the oxidation number of hydrogen? Here, if it's H2O, so now it's not 0 because it's not uncombined with anything else. It's actually rule number 3 or 4? +1, yep. What did we say the oxidation number was for oxygen? -2, perfect. So we can do a little check here, and so this H2O, the formula is neutral. So that means that if I take, let's see, how do I want to do this? 2, I focused on hydrogen first. 2 times +1 plus 1, because there's only one oxygen atom, but it's a -2, that has to be equal to 0. that have to be equal to 0, and it is. We're going to use that kind of technique to kind of backtrack for what's the oxidation number of something if we're not sure. And we're going to start with this one. So, and I just recently, like I said, I'm almost done with part 3 homework. You have some of these homeworks to do. So you start with what you know, and hopefully you end up, you know enough to figure out what you don't know. So I'm going to put a +1 here over my hydrogens. I'm going to put a -2 here over my oxygens. And then, let's see if I'm going to, I guess this will work. So H2SO4 is neutral, so it has to add up to 0. So here we go. I have 2 hydrogens. They are a +1. And I have 4 oxygens, and they are a -2 plus X is equal to 0. For those of you who are into math, there you go. So what is X? +6. Exactly. So do you see where we start with what we know to figure out what we don't know? It's deduction. My dear Watson. It's the end of the semester, you can tell. Okay, so let's do another one. Okay, so I'm going to put a +1 over my NH4. And sometimes, now I remember this, I'm going to put a question mark over my nitrogen. You're like, well, nitrogen, it picks up 3 electrons, forms a -3 charge. Not necessarily. It's not working. This is not an ionic compound, so we can't go there. So if I do kind of like I did before, I have 4 hydrogens. They are +1. And then I have +X. But now it's not equal to 0. What does it need to equal? +1. Exactly. Okay, so what's my X? I'm like a -3. Yep. So it does do kind of that, no? Yeah, it does do like the periodic table, but it won't always, the oxidation number for nitrogen will not always be -3. It is here. Because there's no rule about it. I didn't say you can hang your hat on it. Let's do another one. Okay, so I'm going to put a -2 over my oxygens. And I'm going to say I have 2 oxygens. They are both a -2. And I'm going to put +X is equal to, what's it got to equal? -1. Yep. So what's X? Yeah, so -4. Yep, +3. Now you're like, that's weird. I would have said a negative or -1 or something like that, right? That's a good example of chlorine's oxidation state. Its oxidation number is a +3. All right. So oxidation is a process. It's a verb. Oxidation. During oxidation, an oxidation number will increase. And when I say increase, we're going to be doing some, using some equations to kind of describe this. And it goes like this. Okay, basically we're going to have some element here, and it's going to increase its oxidation number. We call that oxidation. Then, kind of the yang to yin to yang, I'll introduce a Y here. If it's a redox reaction, something's oxidized and something's reduced. So here we go. Between the two, if we come up with their oxidation numbers, this is going to be a reduction in oxidation number. And we call that reduction. That's it. And so actually this pattern is kind of what you're going to see here. as we work these problems. So if something's being oxidized, it's increasing its oxidation number. It's becoming less negative. And that's going to be associated with is going to be losing electrons. If something's being reduced, it's becoming more negative, okay, a lower oxidation number, more negative, and this is going to be gaining electrons. Electrons. That's it in a nutshell. We can go home. No. Okay, so in a redox reaction or an oxidation reduction reaction, you have to have both going on. Now there are some terms that drive me nuts, and I'm not saying you won't even actually, it's potentially you will see them on your final exam next Wednesday. Let's see. Oh yeah. So the thing, I'll just call it the reactant, the thing that you see the formula of on the equation that has actually something that's being oxidized is undergoing the reactant contains the atom whose oxidation number is increasing is undergoing oxidation. Yeah, that's true. That's true. The reactant that has the oxidation numbers decreasing is being reduced. I suppose I'll buy that. That one doesn't drive me nuts. That one doesn't drive me nuts yet. This one drives me nuts. So the thing that's doing the oxidizing actually is being reduced, and the thing that's doing the reducing is becoming oxidized. So the oxidizing agent is the thing that's has the atom that's being reduced, and the reducing agent has the thing that's being oxidized. That's the thing, right? So I would say, let's see if I can kind of go find that up here. I said that this is undergoing oxidation. This would be the reducing agent. Okay, and I said that this is actually undergoing reduction. This is the oxidizing agent. There, I said it. We'll do some examples and double check that we're all on the same page. So we've talked, different types of reactions. We have the exchange reaction, we have the redox reaction, we have the combustion reaction. A combustion reaction is basically where your reactant side, you end up on your product side with oxygen incorporated. Okay, so in that case, it's a redox reaction. So combustion reactions are redox reactions. So I have some videos. This apart kind of in context of what we've been talking about. When faced with this on a test or on homework, what I like to do is I like to scoot along the top of everything and give it an oxidation number. So hopefully for the Fe in its uncombined elemental form, you guys would tell me it's oxidation number 0. This actually, these two oxygen atoms are kind of like, the O2 is like H2, so that's also 0. Life finally becomes interesting over here, where we have the oxidation number we need of those 2 irons and those 3 oxygens. I'm going to put a -2 here because I can hang my hat on that fact. I'm not going to write the math out and all that, but do you see where the Fe would be what, a +3? Yeah. So a -2 for the oxygen, a +3. And kind of like I did here, what I like to do is to draw arrows kind of connecting what's changing. So we see that the iron is going from 0 to +3. It's undergoing oxidation. It's releasing electrons. And the oxygen is going from a 0 to a -2. It's undergoing reduction. This, to me, kind of diagramming what's going on is similar to like drawing a picture for a chemistry problem. And sometimes drawing a picture, you can see things, and actually, in this case, I do this even before I ask the questions. So what sort of questions do we have here? The atom undergoing oxidation, we said, was the iron, right? I think for the homework that's going to be due on Friday, for this part, it says, what's the change? And the change would be +3. Which atom is undergoing a decrease in oxidation number? That would be the oxygen atom. Now, we're picking on individual atoms here. We're not picking on the whole enchilada, the whole reactant product. All right. So the reactant, now this is, when it says reactant, not atom, then you're talking about the whole enchilada. So the reactant that's being oxidized, I know it's a subtle thing, but instead of Fe, I have an FeS. So the solid iron instead of the Fe atom. Reactant that's being reduced would be the O2 gas instead of the oxygen. So the reactant is the thing that contains the atom that's, in this case, being oxidized or reduced. Now again, this is my least favorite thing. So the reactant that is the oxidizing agent must contain the atom that's being reduced. Okay? So if we said that the O2 is the reactant that's being reduced, it is also the oxidizing agent. And so the reactant that's being reduced, or excuse me, the reducing agent must have the atom that's being oxidized, which is Fe. So here, the reducing agent is the Fe solid. It's a very subtle thing. And this actually is showing you this redox reaction that's happening below here. In this case, to me, what I'm focusing on is on the product side, we have solid copper. On the reactant side, we have solid zinc. So, solid zinc, and you've heard of plating, P-L-A-T-I-N-G. So this is kind of solid copper plating onto that solid zinc. So if we take a look at that a little closer, I'm going to do what I did before, kind of scoot across the top, write some oxidation numbers. For zinc, I'm going to put 0. For the copper 2 sulfate, all right, the only thing I can hang, well, I guess I'm going to do it this way. I recognize this from Chem 1 as Cu plus 2 SO4 2 minus. I hope you do too. In that case, we said the copper plus 2, its oxidation number is plus 2. So I'm going to put a plus 2 there. Because otherwise, I have too many things I don't know. For those 4 oxygens, I'm going to put a minus 2. So let's see, minus 2 times 4 is -8. -8 plus 2, that brings me down to a -6. So my sulfur needs to be a plus 6. That makes sense. On the product side, again, I'm going to recognize this as an ionic compound. Zinc is one of those things that you can hang your hat on at forming a +1 charge. So I'm going to put +1 oxidation state here, a -2 again for those 4 sulfurs. And since, 4 oxygens, -2 for those 4 oxygens. And since sulfur is, see, it's like sulfur is sulfate here and sulfate over there, it's going to be a +6. That's not changing oxidation state, is it? Oops. +6. Well, looks like copper is though. Copper is going to be 0 here. So let's see what we got. In a redox reaction, you always have to have something that's increasing oxidation number, something decreasing oxidation number. So it looks like my zinc is going from a 0 to a +1. So it's being oxidized. I'm liking that. And my copper is going from a +2 to a 0. It's being reduced. That works. So to me, once I do that, I'm like, oh, okay, I can answer some of these questions. So the reactant, again, the reactant's not the atom. The reactant is the thing that has the atom in it. So the reactant that's being oxidized would have our, what do we say, this one, yeah, the zinc. So it's just zinc solid. The reactant that's being reduced would have the copper that's being reduced from +2 to 0. So that would be my whole enchilada. My CuSO4, or I guess I'm showing it ionized, so Cu +2 or CuSO4. So now we got to talk about the agents here. So the agent is the thing, so you got to think a little bit opposites. So the oxidizing agent would be the thing that has the atom that's being reduced. So we're looking at, again, the Cu +2. And the reducing agent would have the thing that's being oxidized, which would be our zinc solid. So there we go. Another video of electrons that actually make a gizmo work, right? So actually with regard to your batteries, it's the flow of electrons that make batteries work. And what makes the electrons flow is a redox reaction. Is that not cool or what? Okay. So let's go ahead and we won't do we'll go ahead and do zinc is 0. Those 2 oxygens in MnO2 are -2. That leaves the manganese a +4. Over here, zinc oxide, we got a -2. Oh man. Yep, drat. You guys let me do that too. Okay, so over here, this should have been a +2. I'm sorry. Drat. Sorry, guys. You can hang your hat on zinc forming a +1. No, you can hang your hat on zinc forming a +2. All right. So over here we have oxygen a -2, zinc a +2, and over here in Mn2O3, again those oxygens are -2, so collectively they're a -6. So we need a +6 coming from our 2 Mns. So I have a +3 for each one of those. All right, so it looks like our zinc is going from 0 to +2. So it's being oxidized, and our Mn is going from a +4 to a +3. So it's being reduced. And they're kind of fun. See some videos. First reaction, release of hydrogen gas. The second reaction, kind of the precipitation, that's the AGS. Okay. So I'm not going to pair them up, but let's check this out. One more redox reaction. State. Also for each of the bromine atoms there. And then on the product side, this is an ionic compound, so the aluminum loses 3 electrons, becomes a +3, and bromine picks up 1 electrons, becomes a -1. So in this case, we have on the product side containing the things that are both being oxidized and reduced. So aluminum is being oxidized and bromine is being reduced. Cool. So tomorrow, this is actually, again, we're going to kind of skip part 4 and go to part 5 for a few slides. You guys are going to be balancing equations by what we call the half reaction method. So I'll kind of leave that for a moment. It's fun, but I know like people hate it when I say it's fun. So let's take a look at a few slides in part 5. So this homework will be due on Friday, and I should have it posted to Canvas before I leave tonight. So I mentioned batteries. We're going to take a closer look at those batteries. Something that creates energy from a redox reaction is called a voltaic cell. Okay, we'll be looking more at that. Actually, there's a part 7, I want to say. So we aren't going to get to electrolytic cells, but what an electrolytic cell does is to take energy to drive a redox reaction. So first, focusing on voltaic cells, something that uses a redox reaction to get the electrons flowing to go ahead and drive, using that energy, flow of electrons to drive something. So this will not look like your battery at first, but within your battery it will have these components. So it has what's called the anode, we'll be talking more about that, and a compartment associated with the anode. But at the anode, electrons are released. It will have a cathode and a compartment associated with the cathode. And then at the cathode, electrons are taken in. So hopefully you can already kind of see how that would work with regard to a redox reaction. You need some sort of external circuit to connect it to the thing that you want to energize. Okay, allowing for the flow of electrons that are created at the anode to go to the cathode. And then in order for it to maintain a balance, you need some sort of way to kind of, for charges to get between the two compartments. Some sort of what called salt bridge. Otherwise it won't last very long. So let's take a look at the videos we saw. And it looks like an awkward sort of battery, doesn't it? So here we have an anode in an anode compartment, a cathode compartment. This actually would be the thing that you want to charge. So this would be the thing that you're trying to energize. Instead of energizing something, at least we have a voltmeter up there to show the flow of electrons. This is the salt bridge to maintain the ions. Okay. We're going to be talking more about the chemistry behind individual cells. Here's the thing. Now, not all redox reactions would translate to making a voltaic electrochemical cell, but many of them would. Okay? I just think that is so cool. Down here in this particular place, we have copper here, solid copper, and at the anode, of course, copper is going from a 0 oxidation state to a +2. Silver is going from a +1 to a 0. So there's your redox going on, right? So it's giving up electrons here as the oxygen is oxidized specifically, and we're going to see this tomorrow. Specifically, it's giving up, divide this, 2 electrons for every 2 moles of electrons for every 2 moles of copper that goes from solid to +2. Okay, but the silver is taking in 1 mole of electrons. So tomorrow, what you're going to be doing is breaking out that one equation of interest we saw at the bottom of the slide into 2 half reactions. So we have this half reaction, the copper going from 0 to +2, and then we have this half reaction from the silver going from a +1 to 0. What's different about it, and again we're going to be tackling this tomorrow, is we've gone ahead and shown the electrons. So the electrons are released at the anode and electrons are taken in at the cathode. But one of the things we know about adding 2 equations together is if it's the same on both sides, it goes away. So the net equation here is the equation that you saw before. So electrons released to anode, that amount of electrons will be consumed at the cathode. So one last thing. So here's the cool thing, and it goes from left to right. Well, it's all cool. But it goes from left to right, and it's actually alphabetical. So anode, A before C, anode, then cathode. So what we do is we write what's happening at the anode, then we write what's happening at the cathode. And the copper is going to copper +2. We put a single bar here. We put a double bar between the two compartments. And the silver is going from +1 to a 0. And you can see that right there. So electrode, the solution, electrode.
Will the anode always be the one that's oxidized?
The anode will always be the one, yes.
And so the cathode
Yep.
is always the
Yep. Well, that's a good place to stop. So we'll see you in room 302 tomorrow.